Hi, this is John Whitaker for the Mathematical Analysis 2 class, and this is our 26th video lecture. And we're still talking about sequences of functions converging, and in particular we're looking at convergence uniformly. And I want to start off with the theorem. The theorem says, suppose the limit as n goes to infinity of f sub n of x equals to f of x. And this is for each x in the subspace in subset E. So this is pointwise convergence. And then we put big M sub n equal to the sup over all the x's in E of the norm of f sub n of x minus f sub x. Then the sequence f sub n, as n runs from 1 to infinity, converges to f uniformly on E if and only if the sequence of m sub n's converge to, here I'll just say the limit as n goes to infinity of m sub n's equal to 0, and that's the theorem. Okay, so we want to look at the proof of this theorem. And we suppose the limit as n goes to infinity of the f sub n of x's equal to f of x for each x in E. We're going to put, as the hypothesis say, this m sub n equal to the sup over all x's in E of the norm between f sub n sub x minus f of x. Okay. This statement was an if and only if statement, so we'll prove the forward direction. Okay. So we'll let the sequence f sub n converge uniformly to f we want to show that the limit as n goes to infinity of the m sub n equals to 0. Well, we let epsilon be greater than 0 be given. We need, and this is a sequence of numbers, we need an integer big N such that for all n bigger than or equal to big N, the absolute value of m sub n minus 0 will be less than epsilon. So we want the absolute value of m sub n to be less than epsilon. want the absolute value of the sup over all x's in E, the norms of f sub n of x minus f sub x, to be less than epsilon. Well, this norm here is going to be greater than or equal to 0, and so the sup has to be greater than or equal to 0. And so the absolute value of those numbers are those numbers themselves. So we want the sup as x goes to E of the norm of f sub n of x minus f of x to be less than epsilon. Okay, but since f sub n converge uniformly to f on E, then there exists a natural number n such that for all n bigger than or equal to this big N, the norm of f sub n of x minus f of x will be less than epsilon of 2. Let's say, and that's for all x element of E. Thus, the sup, or I should say, thus for all n bigger than or equal to this big N, the sup over of all x's in E of the norm of f sub n of x minus f of x, that's got to be less than or equal to epsilon over 2, which is less than epsilon. And so that's what we wanted, and that tells me then that the limit as n goes to infinity of m sub n has to be equal to 0. So that's half the proof. Okay, now I have to do the other half. By the way, as I start this second half of the proof, this theorem is stated in our text, but is not proven. And so this is something that's not in your text. So here's the other direction. Suppose the limit as n goes to infinity of m sub n does equal to 0. We want to show that the sequence of the f sub n's converge uniformly to f. Okay. Well, we let epsilon be greater than 0 be given. So what are we looking for? We need an integer. Big N, such that for all n bigger than or equal to this big N, the norm of f sub n of x minus f of x will be less than or equal to. So less than, here the book's been using less than or equal to, but that's the same thing as less than. For, and this is the same as the definition would be, we just had less than. For all x element of E. Okay. Since the limit as n goes to infinity of m sub n equals to 0, then there exists an n that is a natural number such that for all n bigger than or equal to this big N, the absolute value of m sub n will be less than epsilon. And so that's going to give us some implications. So for all n bigger than or equal to this big N, we have that the absolute value of the sup of over all x's in E of the norm of f of n of x minus f of x will be less than epsilon, which implies in this situation where n's are bigger than this big N, that the sup, that's x, the sup over all x's in E, of the norms of f of n of x minus f of x will be less than epsilon. And that implies that the f sub n of x's minus f of x in norm will be less than epsilon. That's true for all little n bigger than big N, and that implies, I'll just rewrite that f sub n of x minus f of x is going to be less than or equal to epsilon, and that's true for all x element of E. And that's what we needed to show that the f sub n converge uniformly to f on E. So that is that proof. Here's another theorem. It says, suppose the sequence f sub n is a sequence of functions defined on E, and suppose that the norm of the f sub n of x is less than or equal to something called m sub n, and that is for all x in E, and for each n equal to 1, 2, 3, forever, then the f sub k equal to the sum as n runs from 1 to k of f sub n converges uniformly on E if the sum of the m sub n's converge. Okay, let's look at the proof. So we're going to suppose, by hypothesis, that the sum of these m sub n's converges. Okay, we're going to let epsilon be greater than 0 to be given. Since the sum of the m sub n's converge, then remember these m sub n's are some positive numbers, and so when we're adding them up to form a convergent series, we have this Cauchy criterion, I think, and that's what we're going to be using here. And so what it says is that then there exists a natural number n such that for all m, this way I know it, for all n and m bigger than or equal to this big N, the norm, this time sets the value, as I runs from m to n of this big M sub I will be less than or equal to epsilon. So since these M sub i's, they're numbers, and not only are they numbers, they're greater than or equal to 0, we have for all n and m bigger than or equal to this big N. So I'm looking at this part. These are all numbers, positive numbers. So you're adding positive numbers, you get a positive number. And the absolute value of positive numbers itself. So these m sub i's is going to be less than or equal to epsilon. Thus, for all n and m, excuse me, and I should be saying this the right way. It's not just for all n and m, it's for n being bigger than or equal to m is what we're saying here for that Cauchy criterion. Okay? So we have some structure on which is big between the n and m, and that's what I should have written over here. But I didn't. Let's go back and change that. So what I'm referring to is this correction here that we're having the stipulation that n is bigger than m. So I should have it here. So that's the change that needs to be made. Sorry. Okay. We have that the norm, as I runs from m to n of f sub I of x, that quantity, is going to be less than or equal to the sum, as I runs from m to n, of the norms of the f sub I of x, taking the sums of those norms, and that's by the triangle quality, extension of it, and that's going to be less than or equal to the sum of the m sub i's, as I runs from m to n, which is going to be less than or equal to epsilon. Thus, for all m bigger than or equal to m, bigger than or equal to this big N, the norm as I runs from 1 to n minus the norm as I runs from 1 to m, each one of f sub I. So the norm of the sum as I runs from 1 to n of f sub I minus the sum as I runs from 1 to m of f sub I. And here, this time I didn't want n being bigger than m. I just say n and m. Okay, so we got two things being bigger than this big N. So that's what I'm looking at. So this difference is going to be equal to, well, it's going to be the norm, and here's going to be a sum. So a lot of these guys are going to cancel out. What's going to be left is from the smaller one of these guys, between m and n, up to the bigger one of these guys. So it's going to be I running from the, it would be the minimum of, I think, m plus 1 or n plus 1, up to the maximum between m and n of the f sub I of x. And then that's going to be less than or equal to epsilon. So that's what we have. So it's using this, that we're having some form that looks like this, which is less than epsilon. Okay? That's what we're having. Okay. Okay. Thus, by the Cauchy criterion for uniform convergence, of sequences, okay, we have that the sequence, I'm going to call it big F sub n, equal to the sum of, as I runs from 1 to n of f sub I, that converges uniformly on E. And that's the proof. Here's another theorem. It says, suppose f sub n converges uniformly to f on a set E in a metric space let x be a limit point of E, and suppose the limit as t goes to x of f sub n of t equals to a sub n. And that's true for n equal 1, 2, forever. Then the sequence of the a sub n's converge. Okay? And not only do they converge, but also the limit as t goes to x of f of x equals to the limit as n goes to infinity of a sub n. Okay. One way of looking at this is to say that is the limit as t goes to x of the limit as n goes to infinity of f sub n of x. So that's this part. It's equal to the limit as n goes to infinity of the limit as t goes to x of f sub n of t. And that's because of the definition of a sub n here. I'm just replacing a sub n what it's equal to. So essentially we're being able to interchange, to switch the order of the limits. And that's being done because of this uniform convergence. Now uniform convergence is able to help us switch those limits. Okay, let's look at the proof. This is very nice. It says, suppose, proof's not, talk's not. So suppose F and n converge uniformly to F on a set E. In a metric space, okay, big X. Then we're going to let little x be, sorry about the notation, this is our space, this is element. So let little x be a limit point of E. And suppose, excuse me, and suppose that the limit as t goes to x of f sub n of t equals to a sub n. Okay. What we want to do is we want to show that the limit as n goes to infinity of the a sub n's equals to the limit as t goes to x of f of x. That's what we want to show. But really, we haven't even shown that the a sub n's converge, and that's part of the conclusion of the theorem. So really, we'll work on that first. So we'll let have something be greater than 0 be given. Okay. Since the f sub n's converge uniformly to f, then we know what that means. There exists an n that is a natural number that's a natural number, big N. such that for all n bigger than or equal to that big N, well, I should say all n and m bigger than that big N. Yeah. And t is an element of E. Okay. We have f sub n of t minus f sub m of t is going to be less than or equal to epsilon. And this is by the Cauchy criterion for uniform convergence. Now, a claim is that the limit as t goes to x of the f sub n of t minus the f sub m of t, that's going to equal to the norm of a sub n minus a sub m. Okay, so that's the claim. Let's do the proof of claim. This is like the proof of claim that we had a couple of days, the last video maybe. And so here, to do this, we're going to let epsilon sub 1 be greater than 0. So I'm going to prove this limit claim. And this is here's what we have. We got this be given. This is the limit of functions claim. Okay. So here we need a delta sub 1 greater than 0, because of limits of functions, such that for all t element of E with 0 less than the metric between t and x being less than delta sub 1, then here we have, this is what we want. We have that the absolute value in this case of the norm of f sub n of t minus f sub m of t minus the norm of a sub n minus a sub m will be less than epsilon sub 1. That's what we want. Okay? Well, let's note that this quantity, this norm, this absolute value, this norm, that's going to be less than or equal to the norm of f sub n of t minus f sub m of t minus a sub n, and then it'd be plus a sub m. Okay, that's something we showed me earlier. Okay, and okay, that's less than or equal to norm of f sub n of t minus minus the norm, minus a sub n plus, so here it would be the norm of f sub m minus a sub m. That's the way that it can be rewritten. And then since the limit as t goes to x of f sub n of t equals to a sub n, then there exists a delta sub 2 that's greater than 0, such that for all t element of E with 0 being less than the metric on our space x between little x and t being less than delta sub 2, then the norm of f sub n of t minus a sub n will be less than epsilon over 2. So that's how we make this part small. Well, similarly, since the limit as t goes to x of f sub m of t equals to a sub m, this should have a t with it. Then there exists a delta sub 3 greater than 0 such that for all t element of E, what's a t? With 0 being less than the metric, the distance between x and t, if you will, being less than delta sub 2, delta sub 3 here, then the f sub m's of t minus a sub m's and norm will be less than epsilon over 2. So we let, I think we were looking for something called delta sub 1. We let delta sub 1 equal to the minimum between delta sub 2 and delta sub 3. Then, for all t element of E with 0 less than the distance between x and t being less than this particular delta, delta sub 1 is what we're calling it. And what we have is this absolute value of this norm that we're working with, norm of a sub n minus a sub m, all that inside absolute value. Well, we know that's less than or equal to this norm of f sub n of t minus a sub n minus the norm of f sub m of t minus a sub m. And then we know that that is less than epsilon over 2 plus epsilon over 2, which equals to epsilon. Okay. And so that tells us that the limit as t goes to x of the norm of f sub n of t minus f sub m of t equals to the norm of a sub n minus a sub m. And so that ends the proof of claim. That ends the proof of claim. Now, since the f sub n of t minus the f sub m of t was less than or equal to epsilon for all n and m bigger than or equal to big N and t, and for all t element of V, all t, element V, then the limit as t goes to x of f sub n of t minus f sub m of t is going to be less than or equal to epsilon for all n and m greater than or equal to n and t element of this big E. And we know what this is, so that tells us that a sub n minus a sub m is going to be less than or equal to epsilon. And that's true for all n and m bigger than or equal to n. That doesn't depend on t. And so what that says, that the sequence of a sub n's is a Cauchy sequence and thus converges. Okay. To a number a sub n. Let's not call it a sub n, I'm sorry, a. Okay. So now we got that, the limit as n goes to infinity, a sub n is equal to a, okay? Now, we now want to show that the limit as t goes to x of f of t equals to a. That's what our job is. Okay, so this is the limit of function here. And so here's what we do. So we've been given an epsilon. So we need a delta, I'll call it delta sub 4, greater than 0, such that for all t, element of V, with, I'm just using the definition of the limit of a function, with 0 less than the metric between t and x and t, doesn't matter, less than delta sub 4, then the norm of f of t minus a will be less than epsilon. So here, note that f of t minus a is going to be equal to, it's kind of neat here, the norm of f of t minus f sub n of t, or in some number, some math number, minus, so here I think I should have written plus, f sub n of t minus a sub n plus a sub n minus a. And now using the triangle inequality, here, here, and here, we have that this is less than or equal to f of t minus f sub n of t plus norm of f sub n of t minus a sub n plus a norm of a sub n minus a. This should have a norm with it. Okay. Now these guys converge uniformly, so I'm going to be able to control those. Remember, I want this whole thing to be less than epsilon. I'm going to be able to control that to make that smaller. The a sub n's converge to a, so I'm going to be able to make that to be small. And then we got to work with that just a little bit, but we'll be able to control it as well. Okay, so since f sub n converge uniformly, okay, to f, then there exists a natural number n such that, we'll call it n sub 1 here, such that for all n bigger than or equal to this n sub 1, that the norm of f sub, the norm of f of t minus f sub n of t will be less than or equal to epsilon over 3. And that's true for all t element of E. Okay? So I control that first thing and the sum, the first of the three things. And then since the limit as n goes to infinity, of a sub n is equal to a, then there exists a natural number big N sub 2 such that for all n bigger than or equal to this big N sub 2, the norm of a sub n minus a will be less than epsilon over 3. Now here we'll let big N equal to the max of n sub 1 and n sub 2. So we push far enough along in these terms of sequences so that both of the things we want to have happen. So we have f of t minus f sub big N of t will be less than epsilon over 3. Say less than or equal to, doesn't matter. So here, this is the sign, okay? Less than or equal to. And the a sub n minus a is going to be less than or equal to epsilon over 3. So since the limit as t goes to x of f sub n of t equals to a sub n, big A sub n, there exists this delta sub 4 that's greater than 0 such that for all t element of E with, I'm using the definition of limit of a function, 0 less than the distance between t and x, less than delta sub 4. I don't know if I've used delta sub 4 before, but this is another number that's positive. Okay? Then what we have is the norm of f sub big N of t minus a sub n. That guy's going to be less than or equal to epsilon over 3. So for all t element of E with 0 less than the metric between t and x being less than delta over 4, we have that the norm between f of t minus a will be less than or equal to f of t minus big F sub n, f sub big N of t,
plus the norm of f sub b n of t minus a sub n, and then plus the norm of big A sub n minus a, and each one of these is less than or equal to epsilon of 3 plus epsilon of 3 plus epsilon of 3, so the whole thing is going to be less than or equal to epsilon. That's what we needed. And that concludes that. All right, ladies and gentlemen, that's enough for this video lecture. Thank you very much.